Hi, I'm Neemesh Yadav and I'll be presenting our work Tox-BART leveraging toxicity attributes for explanation generation of implicit hate speech accepted to ACL findings 24. Our topic, that is to generate implications of potentially hateful text, is majorly motivated due to the dire and increasing need for reading online content moderation. In this attached figure, we can see that both the toxicity and target prediction APIs benefit a lot from the extra context provided in the form of this stereotypical implication of this given text. Previous work has also shown to be increasingly reliant on using knowledge graphs for solving domain-specific tasks such as ours. We wish to uncover how useful are these methods apart from just looking at the metric source. We also explore other alternatives to using knowledge graphs that is relatively more sensitive to small changes. We try to answer two main research questions in our work. First is how relevant are the quality of the knowledge tuples. Intuitively speaking, this score should hurt if the quality is changed from most relevant to least or random sampling. We also hypothesize that the process of obtaining knowledge graph tuples is task agnostic and may not account for the multi-hop and indirect nature of it. Our second research question is, are there any alternative signals in the form of toxicity attributes that are comparable to knowledge graph infusion? And how sensitive are these attributes? So we perform all our experiments across two datasets, SPIC and latent hatred. SPIC is a majorly explicit hate dataset with each sample having one or more gold explanations, whereas latent hatred is primarily for judging implicit hate. In latent hatred, each sample has exactly one gold explanation. We used the classic BERT, Goyal, and BERT score metrics to remain consistent with previous works. In research question work 1, we explored two kinds of knowledge graphs, ConceptNet and StereoKG. ConceptNet is a huge general domain common sense knowledge graph, whereas StereoKG is a much smaller but very specific knowledge graph made for storing stereotypes against 6 religions and 6 nationalities. Due to the high number of tuples in ConceptNet, using cosine pair similarity for extracting tuples was not a feasible method. Hence, we relied on using the method proposed by Chang et al. 2020 to query it, which was to use weighted TF-IDF over the uh, whole whole dataset that we have. Now, knowing about mixin is a bit important for our work as we build heavily upon this. This is a knowledge-enhanced BART model proposed by Sridhar and Yang in 2022 that leverages three kinds of knowledges: expert, which is essentially just the expert annotations of each dataset; explicit, which refers to the knowledge graph or knowledge graph basis; and implicit knowledge essentially means the latent knowledge stored inside each model. We primarily focus on explicit knowledge due to the heavy attention on using knowledge graph infusion in other previous works such as Lin 2022 and Chang et al. 2020. Now in this section, I'll discuss our results and observations of experiments found for RQ1. In our experiments, we simply concatenate the knowledge graph tuples to the input post with a separator token. This method has been shown to work better than using attention modules by previous works. Across the board, we choose between extracting the most or top relevant, least or bottom relevant, and randomly sampling from the knowledge graph. As visible from this table, the quality of knowledge graph is inconsequential to the final results. To confirm this hypothesis, we also show that this is valid for stereoKG, a domain-specific knowledge graph which is well suited for our task as it was created primarily to store the stereotypes, and our topic is to generate stereotypical implications. Now, we also wanted to do a manual analysis of this hypothesis just to confirm it once more. So two annotators were selected to perform a manual analysis of these extracted tuples to see how relevant they actually are for these posts. Each annotator rated the quality of these tuples based on two metrics: task domain relevance and general domain relevance. Task domain relevance, or TR, in the table determines how effectively the retrieved tuples can explain implied stereotypes. General domain relevance, or GR, in the table determines if the tuples capture diverse concepts enlisted in the sentence from a common sense or word sense and or word level understanding. Here, here TR refers to a more domain specific. Here TR is a more domain specific metric. So we are trying to answer if this these tuples would be useful in the sense that we are solving this task of generating stereotypical implications. However, GR is the contrary to is a contrary to TR. Uh, we are trying to see if these tuples even make any sense, uh, independent of the context in which we are trying to we are extracting the tuples, right? So we show that the quality of extracted tuples themselves are not that informative or specific to our task, which calls for better retrieval methods. Here I'll be discussing our proposed methodology, results, and some error analysis. This attached figure shows a rough pipeline of the methodology we propose. We introduce two kinds of attributes, in-domain and in-dataset toxicity attributes. The in-domain attributes refer to domain-specific tokens generated using a BART model trained on the jigsaw and intended by the dataset. The model is trained to predict tokens such as toxicity, severe toxicity, the lewd nature of the text, the offensive nature of the text, etc. etc. And the in-dataset attributes are the meta attributes already present in the dataset. For instance, the speaker race attribute, which tells us about the race of the speaker minority attribute, which tells us about the minority, which tells us if the speaker is a minority or not. The implicit type attribute, which tells us what the nature of that text is it incitement or etc. etc. Right. We experiment with multiple configurations for the in-domain attribute, which I will now explain next. So C1 is our main configuration for using in-domain attributes, and C2 in the next table, in the next section, refers to the in-dataset attributes. C3, 4, and 5 are some ablations we experimented with for in-domain attributes. In C1, Tox-BART generates the probability of each signal for some given input post. These signals are then thresholded to be converted into special tokens that such as toxic, not toxic, severe toxic, not severe toxic, if the probabilities is greater than some lambda function or not. Right, and these tokens that we now produce are then simply concatenated to the input post, and which is then passed on to a BART model to generate the final implications. In C2, however, there is no such use for toxic BERT because we are simply concatenating the tokens from the special columns to the input post. So essentially, we simply concatenate the meta attributes from different columns to the input post in C2. And C1 is pretty similar to how we performed our experiments in RQ1, because in RQ1 we concatenate the KG tuples, but here we are concatenating tokens that we produce using a toxic BERT model. Now these results in the first table show that our methods are highly comparable and prove to be a good alternative to using knowledge-based methods, to using previous knowledge-based methods such as implicit knowledge, explicit knowledge, or using both explicit plus implicit knowledge. We also did some interesting ablation studies, which you can find in section 4 of our paper, where we found that these attributes that we propose are very sensitive to varying probability of signals. Interestingly enough, flipping the signals of of a specific attribute, that is severe toxicity, actually leads to a much better performance than any other model that we experimented with in this work. And we also did a human evaluation over 17 samples across 20 annotators to compare our method with GPT 3.5, which was at the time the state of the art LLM. Uh, we found that our method is much better in being specific and to the point, but at the expense of being a bit toxic, of having high toxicity scores. We hypothesize that this specificity comes at a cost of explicitness, which will be very useful to content moderators. In the first table of this section, we show a few samples where our method generates much better and specific implications in comparison to GPT 3.5. Uh, and in the second table, we show how our method suffers from four types of errors, that is, hallucinating the stereotype, generating an incomplete stereotype or an empty string, predicting the wrong target group, or due to the unfortunate consequence of having incorrect or incomplete annotations in the original dataset, and having subjective annotations, which are essentially having multiple annotations, which can be true, but each annotation is due to each annotator's independent knowledge and prejudice. Now, to conclude, we examined the effectiveness of knowledge graph infusion methods. We raised the dire need for domain-specific retrieval methods, and more discussion along language model integrity is needed. We propose a methodology as an alternative to using knowledge graph infusion that is much more sensitive to altering signals. And in comparison to GPT 3.5, our generations are much more sensitive, are much more specific, but more toxic and explicit, which we hypothesize can be used by content moderators to maintain a healthy platform. Thank you for listening.